Welcome to press class number 93, and today we're finishing the Lattice Boltzmann series we had in 91. We're looking at the high-speed trained noise using the LBM CFD method to determine what the noise is to simulate it. And we're looking at this paper called Numerical Analysis of Aerodynamic Noise from Pantograph in High-Speed Trains Using Lattice Boltzmann Method. And this is an open access paper which you can find in the link in the description. So we left off on page 7. Up until then, we were looking at how they set up the LBM CFD. And we were looking at some different validation cases they're looking at, for example, the square cylinder. And then we looked at the noise that they generated from this pantograph. Let's just recap what the pantograph is. So if you haven't listened to podcast number 91, go back and listen to that, but just briefly. The pantograph is the point at which the train connects to the electricity cables above. So it's that like wire that sticks up at a funny angle. And there are a few different parts to the pantograph. So you have the joint, and then you have the base, and you have the head, and then you have the different arms connecting these different points. And we actually finished off last podcast talking about how directional certain noise is. So for example, with this pantograph, we found that depending on where you were standing around it, the noise would be different and by significant amounts. So the minimum was 102.3 decibels. The highest was 107.6 decibels. So that's a 5 decibel difference, which is huge. It's not just like an extra 5%. It's it's a doubling effectively with the decibel system. So I just also want to recap the direction for the direction axis that they're using here, because we're going to use it later in this podcast. So when they have an NX, NY, or NZ, so the N in front of it means that it's either pointing upstream to the right or down. When it's PX, PY, or PZ, it's the exact opposite direction. So it's either back, to the left, or up. And this is important because they have different directionalities later on. So let's continue with what they're looking at. So in figure 18, they say it was confirmed that the highest noise was generated in almost all frequency ranges from 0 to 20 to 10,000 hertz. Sorry. As shown in figure 18. So they have figure 18 here, which has the sound pressure level in dBA, which we covered earlier was weighted for human hearing. And the frequency ranges from 20 hertz up to 10,000. And all these different aspects, so the pan head itself with all different directions have different noise propagation. So for example, in the PY direction, which is upwards, there is a lot more noise at low frequencies than any of the other directions. Whereas once you get to higher frequencies, they sort of mimic each other a little bit, but for some reason the pan head, so the top two bars, that structure there, that connects directly to the wires to get electricity, when you go above that, you're standing above that, let's say, there's a lot more noise from it for some reason, whereas the other directions, the noise is significantly lower. So they say that the frequency range of the dominant noise was from 200 to 800 hertz, which interestingly enough comes mostly from that standing above the pan head. The other directions are not as powerful. Furthermore, it is noteworthy that a peak at 242 hertz occurred in the upper direction of the pan head. So that's a tonal noise, and tonal noise is potentially more annoying than broadband, depending on which frequency it is. So in figures 19 and 20, they say that to investigate the noise generation mechanism, DNS, which stands for direct numerical simulation, using a two-dimensional panhead was constructed. The flow in the panhead section had a continuous vortex shedding, as shown in figure 19. So this is effectively just von Karman street. And von Karman streets are good in terms of they're very predictable. They're bad in terms of that they are tonal in terms of noise. This is all done with a Lattice Boltzmann method, by the way, which we've done other podcasts on as well. So, moreover, the peak of the sound pressure about the two-dimensional panhead is considered in the considered frequency range was at the same frequency, 242 hertz, as the upper direction of the panhead as shown in figure 20. So in other words, when they were doing the three-dimensional simulation, they found that 242 hertz was a tonal noise, and that was one of the worst noises generated. They also found this in a two-dimensional simulation. So it shows that this von Karman shedding is responsible for that 242 hertz. Now, this is one thing that's very difficult sometimes for noise, for acoustics, trying to figure out where this noise is coming from, because if you're measuring it from far away, sometimes it can be just all jumbled together. And we'll talk about an experimental way to do that later in this podcast as well. But we'll get to that after we finish this LBM section. So in figure 22, they have sound pressure level generated from the joint. So this is halfway up the pantograph. So you have a base, then one arm going up, then another arm from that arm. But where those two arms meet, that's the joint. They have the sound pressure level generated from this joint, and it was between 90.3 decibel dBA and 103.5 dBA, so a 13 decibel difference, which is huge. And if you're standing in front of it, the noise is much greater than if you stand behind it. But if you stand left either side of it, it's about the same. So at the joint section, the noise spreading to both sides was larger than the back and forth direction, though. So even though the front direction was, for some reason, emitted a lot more noise than the back, those two noise sources were less than either side. So standing to the side of the train is much more noisy for you. And then they have figure 3, which shows the noise characteristics of the joints. So they have the frequency range and the sound pressure level in dBAs in the y-axis for the upstream of the train, downstream, and left to right. They say that the dominant noise frequency range was between 200 and 800 hertz again for this joint section. It's not only is the pan head, which is those two bars above, but also the joint. They're producing all this noise in the lower frequency range. Interestingly, the upstream part of the train in this, sorry, the downstream section, so if you're standing downstream of the train, you get a lot less noise than any other direction around the train by like 10 or over 15 decibels. That's a major reduction. If you want to reduce the noise of a train, I guess you could just stand behind it. And then in figure 24, they show the sound pressure level propagation from the base section. So the base section is where the pantograph connects to the actual train itself. And this is a fairly variable section because you can have like a recess where you put the pantograph into the train, or you can have an air conditioning unit around it, which then changes how the flow affects the noise generation. But they say that the sound pressure level generated from the base section was between 99.8 decibels dBA and 104.9 dBA, as shown in figure 24. The base section had the noise spreading to both sides in the direction of the flow. So in other words, standing either side again of the base section, you're going to get the same amount of noise. Standing upstream compared to downstream, you're getting a little bit more noise. So that was a similar sort of thing we found for the joint section. But with the panhead section, which we were looking at in the last podcast, we just finished off the panhead section, we found that for some reason, downstream was significantly louder than upstream, and every other direction was about the same in terms of the noise generation to upstream. So for some reason, just downstream, there was a lot more noise from the two bars of the pantograph. So the pantograph itself propagates noise very differently depending on which section you're looking at. And they found this all with CFD. Now let's move on to the field testing analysis. And the reason why I want to look at this is because they look into something called a beamforming. And this is important because you know how I was saying just before, how trying to figure out where the noise comes from in a system can be very difficult, because if you're just standing like 5 meters away, or then you should be 1 meter away with the sound pressure level standards, but let's say whatever distance you are away from the source, and you have your little microphone, you're standing there, well, you have one point to measure the noise, and you don't know where this noise is coming from. It could just be anywhere. Beamforming, on the other hand, this is a very cool technique where you have a bunch of microphones dotted around the place, and you determine how out of sync these microphones are with each other with a noise source. From there, you can then pinpoint where the noise is coming from. And that's very cool. So they say the main noise source in the pantograph can be considered as complex aerodynamic flows around the structure when running at high speeds. As we saw, the noise coming from the pantograph, the joint, and the base sections are all different. So trying to decouple all these sections, it can be difficult. That's where this beamforming section comes into it in experimental results. However, it is difficult to derive the pantograph noise from the noise of the whole train when running at high speeds. Therefore, in this study, sound visualization results of the high-speed train were used to compare the propagation noise from the pantograph in the up and down modes under the same operational conditions as in a real high-speed train. The microphone array that they used had 144 channels in a spiral configuration, as shown in figure 26. So what this is, imagine for those listening to this, imagine a big circle, and you have these microphones dotted around in a spiral fashion. Now, this is the beamforming array, and they have 144 microphones. Now, I'm not sure why they used this configuration because I've seen other beamforming configurations which just have um, effectively equidistant microphones dotted around um, the area of this circle. So putting it in this pattern, I'm not sure why they did it here. If you know, let me know in the comments below. So they tested in real life a Korean high-speed train. They have a track here, which they went out to, and they have this big beam-forming array. And they say that Korean high-speed trains generally run at a maximum operating speed of 300 kilometers per hour. I think that's a little bit slower than the Japanese high-speed trains, so the Shinkansen, which I think go up to 340 k's per hour, I think. But they're both quite fast, and there are other ones around the world which are around the same speed. Therefore, simulation analysis was carried out at the maximum operating speed. However, the tested high-speed trains were designed to reach a speed higher than that of the conventional high-speed trains. So, in particular, this train was able to run in the down mode of the pantograph in the operation line. Under this condition, the high-speed train traveled without power supplied from the cantery. So, what this means is, imagine the high-speed train with that pantograph section, the stick sticking up. They can lower that and still run along. They say that in order to distinguish the pantograph noise from the noise of the whole speed train, so in order to distinguish the pantograph noise from the noise of the whole train when running at high speeds, the propagation noise was measured from the pantograph in the up and down modes. So they had the train running with this pantograph up, and then they had it running with it down, so they could distinguish between the two to decouple them. Now, a word on this, that's a good way of determining the primary effects of each component. So the primary effects of the train and the primary effects of the pantograph. But there's something called a synergistic effect or a secondary effect, or even tertiary when you couple it with other things. And this is when you have both of these things together, they have not only their own noise propagation, but noise being produced because of the interaction. So one very simple way to look at this is, let's say you have two cylinders, one upstream and one downstream. Now, if you were to just have one upstream and get rid of the one downstream, and you measure the von Karman street and the noise coming from that, you'll get a certain value. Then you get rid of the upstream one and just put the downstream one in, and you do the same thing. So you're going to get two different noise sets, spectra for these things. But then when you put them together, you're not going to expect to get the superposition of these two spectra, because you're going to have the upstream effects impacting the downstream cylinder, and it's going to change that noise propagation as well. And also, even the downstream flow physics might affect the upstream flow physics, and that's going to change that too. This is called a secondary effect. So you can't get an entire picture of what's happening just by measuring something while removing another object, and then vice versa. You have to look at the secondary effects as well. And to do that, you can do something called a design of experiments, where you carefully plan your experiments to look into the primary and secondary effects based on different configurations. So for what they're doing here, it's great to look at the primary sources of the noise. In figures 28 and 29, from the noise mapping results of the pantograph in the up mode at 350 k's per hour, the main noise source, such as the wheels, intercoach spacing, and pantograph, are shown in figure 28. So they have a really cool figure here showing the amount of noise at different frequencies. 250 hertz, which was the 242 hertz was the frequency which the pantograph was giving off a lot of energy, or a lot of power. So 250 hertz is quite close to that, and we can see that there are a bunch of different hotspots. Then as we go up in frequency, the power drops dramatically. So it's really in the low frequency range that these pantograph structures are producing a lot of noise. In figure 29, the noise mapping results of the pantograph in the down mode at 350 k's per hour are shown. And we still see quite a lot of noise coming off at the low frequency range, but not nearly as much. So you can see that like all that red high power regions, they're reduced. So the train is producing different frequencies and different noise compared to the pantograph itself. They say the measurements were carried out under the same conditions except for the pantograph being down. Moreover, because the pantograph in the down mode was in the pantograph cover area, it was difficult to generate aerodynamic noise from the structure. So this was talking about where the base section, depending on the configuration, the pantograph itself could produce a lot different noise depending on the structure. So when you put the pantograph down, it could be completely covered by the base section, in which they were saying here. So it's not a factor in terms of noise production when it's in this down configuration. So, according to the two comparison results of exterior noise measurements using the microphone array or the beamforming array, the noise of the pantograph was dominant in the low frequency range below 800 hertz, and let's even lower than that. I mean, when we have these noise maps, we can see that the noise is really coming from 250 hertz or less, like 315, 250 hertz. At 800 hertz, there's almost no noise. There's a few little noise spectra, noise generations areas around the intercoach spacings, which could be because of the intercoach spacings, or it could be because the pantographs are located often at the intercoach spacings as well. So we're talking about how the pantograph, when you put it down, it could be hidden by that base area. But that base area itself, which could also be the air conditioning unit, could be producing noise as well. So that whole structure is very complex. They say, as a result of the simulation, it can be confirmed that the low frequency noise is generated by the pantograph region, which is very true. Now, there's also some synergistic effects which could be looked into in different studies. So that's the end of this podcast. We covered the rest of the Lattice Boltzmann method, and we showed that it's predicting the same general frequencies as the experimental results, where in this experiment, when they had a beamforming array, they found at 250 hertz, which is about the same as 242, we get a lot of noise from these high-speed trains in real life, which is really cool because it's not very often that CFD for Aeroacoustics mimics real-life situations, especially something so complex as a high-speed train going in a field somewhere. But the LBM CFD could do that. At least they get the frequency right. In terms of the decibel levels, we didn't look into it in this paper, but that could be a later topic to look at. And then in terms of just the general noise coming from a high-speed train, they found that the pantograph is a dominant source of noise. Considering how small it is, it's very pesky. And the rest of the train is producing more broadband and slightly higher frequency tones. And not tones, but noise. It's not tonal, really. So that's in this podcast. Make sure to like, subscribe. And if you want to get better at CFD, then check, or theory as well, like this, check out our courses and link in the description. And if you want to get your experiments to be more accurate and your CFD validation data to be more accurate, check out the Atmosphere Hawk, because this measures the density of air, and the density of air changes by about 2 to 4% every day. So if you're not measuring the density of air in your experiments, then your data will be about 2 to 4% wrong throughout the day. Between days and between weeks and between seasons, it's even higher. So you can get up to like 10 or even 15% on extreme days and seasons. So the Atmosphere Hawk gets rid of that error for you. And check out the instrument in the link in the description. And I'll see you in the next podcast. Peace out, amigos.